Hi, my name is Rolf Muralt. I've led product management at Pluribus Networks for the last 3 years. And basically, I'm passionate about how software is changing the data center. So what I'd like to do today is to just give you a little bit of an overview of a fairly wide dynamic range of some of our use cases with customers. Feel free to ask questions. It's not entirely scripted as maybe some of the past presentations have been. One of the things obviously we're doing is changing networking in terms of enabling some software-defined networking features, network functions virtualization. But the way I like to think about it is our platform is more of a converged compute network storage device in that we enable transport-aware applications. And so the use cases that I will show you is essentially customers that have seen the value of this convergence and writing applications, distributed applications for the most part, that they would not have been able to do otherwise. So the first one, squarely SDN, right? Stanford Defined Networking. And so at Stanford, we are supporting OpenFlow. And as Sunny mentioned, we are supporting OpenFlow more as a northbound API. And so we actually see that our clustering enables OpenFlow to scale better. But the use case at Stanford I'd like to talk about is actually us as the entry switch into their electrical engineering buildings as well as the computer science building. And in that application, the Pluribus network switch is running a workload, which is a network monitoring workload. This workload comes from a partner company, which is called Quotient, which is based out of New York. Works a lot with the three-letter departments, but has an open source version of this software. Stanford uses the Pluribus switch to handle the traffic coming into the building, but then enabling the network monitoring application to get a subset of the traffic, do flow analytics on top, store all of the flows in stable storage, which they export off of the switch. So some of the benefits of this architecture is essentially that we allow not just one instance of the network monitor application to run, but multiple instances. So as you deploy virtual networks, each virtual network can get its own monitoring instance, and the management of that instance can be handled by separate teams, which is the case at Stanford. One of the challenges with network monitoring is that past 1 gigabits per second of line rate, it becomes very, very expensive. A lot of solutions require the aggregation of taps. You need a separate network. You then need a whole bunch of servers to handle the processing of these flows. We can do with the model that Stanford has deployed up to 10 gigabits per second of network monitoring. But we have platforms which are coming in a few months which can do up to 40 gigabits per second of network monitoring. So as people are going past 1 gigabits per second to 10, 40, and 100, we think this is a rational economical path to actually handle security within the network. The application is today saving, so the way we ended up thinking about the TCO was, when Stanford has an attack and they have a possible exposure of some of the data, they need to make a decision as to where this gets escalated within the school. So the savings that they're seeing is not so much the convergence of appliances, having less servers, having less storage. It's the fact that they're saving on the legal bill of what the central Stanford resources is going to spend on any given instance. So we call that the mean time to innocence. If they see that there is no exposure of a certain resource, the escalation can stop. And so that's really the large value that they've seen in the system. The second example I'm very excited about in terms of how it shows both hardware value and software value in the Pluribus systems. And essentially, Cloudflare today handles 5% of all internet traffic through the Pluribus network, and I'll show you what the global fabric looks like. But this 5% of traffic is going through our switch, where we can basically give some special SLAs to a subset of the packets. One of the things that Cloudflare found was, as they migrated from 1 gigabit per second switches to 10 gigabit per second switches, is all of the top of rack switches today are designed with single chip merchant silicon that has very limited buffering. Generally in the data center, you don't need that much buffering because you tend to have sort of a low latency feedback loop. You tend to not have congestion. You can afford to over provision because the cost per port is coming down, the cost per link is not very high. If you're in the content delivery network environment, your uplinks, that capacity is going to be a lot more expensive than the capacity within the level 3 colocation. And so being able to give special SLA to some of that traffic so that you're not retransmitting in the low bandwidth, high latency part of the network is critical. The other piece that we essentially enable Cloudflare to do is they see which packets are being affected. They see distributed DDoS attack as it is happening with microsecond level programmatic APIs that can give them this information. And so Cloudflare's value on top of being sort of a content delivery network is really to protect users' websites from DDoS attacks. So having the ability to respond very quickly is key, and having the ability to reroute the traffic is key. I should probably mention when I was mentioning the hardware. So they use our 2 platform, which has a network processor unit, which is essentially what is enabling this increased amount of buffering as well as SLAs. This is what Cloudflare's network looks like. You know, we think about SDN generally within the data center. This is a global fabric, right? It's a worldwide fabric, 25 different nodes in this fabric across the world, but real-time and analytics across all of these nodes. Another interesting example that is a very exciting environment for us is essentially the emergence of people that are building clouds that are not necessarily like Amazon, right? Building clouds which enable workloads that you could not put in the cloud today. And so we view that this financial services cloud is sort of one example of a trend of these more specialized niche clouds, which require a lot more insights from the applications into the transport layer. In this case, the cloud was built as sort of a next generation of high-frequency trading infrastructure. Typically, HFT environments have been sort of hand-rigged, you know, small scale, sort of the Wild West first approaches into financial trading. As more players enter the market, as there is now hundreds of different exchanges, people are finding the need to essentially consolidate some of the infrastructure and share it amongst multiple tenants. But they still want low latency. They still want very tight control of which packets get to be seen by the application, which headers get to be rewritten. And so this is what we're enabling for this financial cloud builder. A very key aspect is the resilience of this system. And so the ability to have very fast failover in the face of component failures. As any cloud application, it is designed with scale-out object storage. So we have certain parts of the file system, scale-out object file system that is running in the network natively. So our Sandy Bridge processors and our devices are actually executing some part of the workload to enable lower latency, faster storage. One of our first, this is something that's been in production for 2 years now. This is an incubator that is essentially providing the infrastructure to all of its portfolio companies. Its portfolio companies tend to be in the OpenStack or, for the majority, Hadoop big data space. And so there's been an interest in essentially no longer building dedicated silos for Hadoop big data applications. However, Hadoop is still one of the workloads where people don't want to take the virtualization overhead. They don't want to pay the hypervisor tax, if you will. And so we are enabling, with our virtual networking infrastructure and the storage that we can connect to each VNet specifically for each tenant, we are allowing a full rack to be managed by the Pluribus Networks device as if it were one logical entity. So what happens is, as the customer needs more capacity, they go in and rack an additional compute resource, and it gets associated to the appropriate virtual network, and we will bare metal install the underlying operating system as well as the Hadoop workloads that live on top. So we call this our platform as a service use case. The interesting piece with this is, if you have 50 servers in a rack and one tenant needs additional capacity, traditionally you would have to go to storage to install the image on one of the servers at a time. Because we control the broadcast domains within our switch, with one image access that lives in the network, we can in parallel bring up all 50 servers in parallel. It's a very, very flexible way of reassigning the same compute hardware resource from tenant to tenant within literally seconds. So with the Fusion IO option that we support, we can literally bring up a full environment in a matter of 10 seconds. TIBCO was our first OEM customer. This is essentially a representation of their device. It's standard, essentially, hardware as our systems employ, with some additional options for their high-end in terms of Fusion IO cards. This is the very low latency messaging solution, and they also have their standard EMS enterprise messaging system stack, which is running on the server switch. So one of the benefits that people very quickly latched onto was, if you build this sort of appliance, you gain a latency advantage, right? The application is running closer to the network, there's a latency advantage. But what I thought was interesting to maybe show you is that it's actually a fairly small part of the overall picture, because if you think about how messaging is deployed, it's a distributed application. Distributed applications always tend to have primary and secondary workloads, servers. They need to synchronize state, and that makes writing distributed applications very difficult. The way that generally state is synchronized is by writing to a common storage array, right? Big, expensive storage array, not very high bandwidth, low IOPS, high cost. What we can do with a fabric view of the network is to say, well, let's put the storage in the network. It's scale-out storage. You're getting the economics of scale-out storage. And the fabric operating system will provide the common single point of management for that storage. So split brain problems become a lot more tractable. Lots of advantages in terms of being able to add extra nodes without actually having to rewrite the application stack. There is obviously a very important latency benefit. The topology in the bottom right is based on TIBCO's low latency product. So basically under 2 microseconds of this is based on RDMA of client server message passing between the different devices. So essentially about a 5x acceleration from what you would typically see.
So this model is really interesting because there's another vendor in market who does, I don't know if it's an ASIC or a programmable chip, but effectively binary level code development that allows them to access and do things with data right on the switch.
Yes.
The problem with that is there was a super high cost to that development. It's it's not a very nimble development process because of how low level it is. And even though there were C compilers and stuff back to it, it still was an abstraction of that.
Yes.
So one of their big use cases for that was you have this huge amount of data that you've got to collect because of the type of data it was, but you only want to take action on a certain amount of that data. So what you want to do is you want to apply high speed processing on the switch, let it rep that down to something else, and then pass that filtered data on. with what you guys are doing and with the subsystems and how you guys have gone this bare metal approach, are you fast enough to do that type of interaction, but with real usable code structures like C and stuff like that?
Right. So you know, in general, the way I tend to view our server switch is as a gearbox, right, in a car, right? You have the very fast speed stuff that's happening on the switch chip, and for the algorithms that we can run in the switch chip, we will run them in the switch chip. In the TU model, we have a network processor, right? So we have about 100 gigabits per second of capacity. And it becomes a little bit more involved to program the animal, right? And so we provide the API that essentially will do the mapping for you. We actually do support dedicated FPGAs as well, because we have PCIe cards. So if somebody wants that environment, they can absolutely have that environment, and we map that PCIe card into the operating system space and the users.
So for that real-time stuff, you've still got to go back to the binary level FPGA stuff in order to get it.
They can absolutely absolutely do that, right? So the flexibility is there. But I will tell you that what we saw with the financial services cloud is the number of algorithms that they can execute and turn around in an FPGA is trending to zero, and economically it's definitely not that attractive anymore to do that, because the cycle time is too long. They find the algorithms change too fast, and so this financial services cloud used to be in that business and made a conscious decision, which was that this was not the way things would go in the long term. Eventually, these small arbitrage opportunities that you could do on an FPGA would not be the 80% of what the workloads was that people wanted to do.
Okay.
Any so this is all I had. So I'm happy to take some questions.
The TIBCO product is the chassis with the Marvell MPU. Is that right?
Yes, it is.
And are they leveraging that for stuff?
They are not leveraging the NPU today. So essentially, the part that they're leveraging is our API, right? It's the NetWiser API, and we have enabled them to essentially have a synchronous write to multiple systems. So whenever they deploy one of these units, they always deploy them in pairs. But to the application, it looks like one target. So every message makes it once and exactly once into stable storage on both devices, and that's the key to doing the 100% persistent guaranteed messaging. That is the foundation of enterprise messaging.
Are they deploying it just as the messaging bus, or do they have the rest of the value add stuff from, you know, Reuters or any other, you know, sort of ticker plant company in there?
So this does not do ticker plant. This strictly does what the EMS product is, the messaging product. The FTL, faster than light product, is essentially a lower latency version of it. For the ticker plant, one of our other customers is essentially using acceleration card to do that piece. So that's where the PCIe piece comes in.
Just the guaranteed delivery on the messaging bus is huge, because I mean that thing is, I don't know, working with the messaging buses feels like being a, you know, bomb disposal tech.
Yes.
It's really volatile and dangerous, you know?
Yes. Yeah. So this is, you know, essentially EMS has been shipping for about a year and a half now. So it's in production, you know, a number of you know, hospitals, you know, number of sort of high profile places. Okay. Thank you.